I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, this opportunity we have to meet and study your creation. Just pray that you'd give us insight about potential today and just guide our steps, Lord. In your name I pray, Lord Jesus. Amen. Yes, so we have talked about Coulomb's law, Gauss's law, right? And we've seen how those are interlinked. And now we have come to the point of thinking about the next step, right? Which is potential, right? Now, of course, you guys may remember from your previous course, potential is, roughly speaking, potential energy per unit charge, right? But we're kind of take a more, I guess, basic mathematical tact with it to start with. And so the first order of business is just to talk about the curl of the electric field. So, potential. All right, so there's a fundamental lemma. And that fundamental lemma is that if we calculate the curl of, my separation vector is degrading, r hat over r squared, right, this thing, we can see that that's equal to 0, at least where it's defined. Is defined. Now, I don't want to get into trying to, figure out whether or not there's a hidden direct delta there or something. I don't think so. But now here, of course, the script r vector is going to be r minus r prime. And as usual, we have in mind the application that this is the field point and this is the source point, right? And the thing is, we talked last time about how the electric field can be built from integrating, right? I guess I should bring the 4 pi. Integrating 1 over 4 pi epsilon naught, right? We take the integral of rho of r prime, d tau prime, I suppose, and that gets put in the r hat over r squared direction, right? And where is this integration done? It's done over all space, right? So I'm not even going to write that. It's just understood. This is the integral over all space. We just let the charge density be 0 wherever the charge isn't, which is a way of changing every finite integral into an infinite integral. That's kind of dumb. So we don't have to say we just let the density do the work in terms of describing where the charge is, right? So this was, we actually worked this out, right? We found electric fields from integrating this over, the line charge, the ring, the disk, and such. But okay, so if that's the case, we can calculate the curl of the electric field in light of this formula, right? And so if we calculate the curl of the electric field, we've got 1 over 4 pi epsilon naught integral of rho of r prime d tau prime. I'm just, where you put the d prime is irrelevant, all right? It's just there somewhere, okay? The point is that this curl, right, is taken with respect to variation of the field point, not the source point. And as such, nabla is actually x hat partial partial x plus y hat partial partial y plus z hat partial partial z, right? That's the del, the vector operator. And as such, this calculation goes, I just bring nabla inside and it hits this unit Coulomb deal here, right? The r hat over r squared. But by the fundamental lemma, that is 0. You see? This is 0. And as such, the curl of the electric field is 0. Do you guys remember the significance of that from like Calc 3? What's the significance of the curl being 0? What's that mean?
Conservative.
It's conservative. What's the context of that?
It's path irrelevant.
It's okay, that gives you path independence. That's, I mean, here's a quick walk down memory lane for you guys. The following are equivalent. Number 1, f is equal to the gradient of some little f, right? Number 2, the integral over c1 of f dot dl is equal to the integral over c2 of f dot dl for all coterminal paths c1 and c2, right? Point number 3, the integral around any loop of f dot dl, it's a 0. And then point number 4, the curl of f is equal to 0. These are, but the thing is, the following are not equivalent. That's a lie. Okay, so first of all, this has to all have context, all right? The domain matters. So let me like add that on, you know, let me say S for space on some space S. C12 in a space S, all right? Any loop in S. And down here on S. But if I want to add number 4, I need to have at the start of this for S simply connected. And the reason I need that is essentially the connection between like the 4th one and the 3rd one is supplied to us by Stokes' theorem, right? Stokes' theorem says, you know, if you've got some loop, right, and it's bounding some surface, which I guess I'll use, I don't want to use S for, I got to use something else, P, all right? So this is inside the larger context of the space, all right? If we calculate the integral of around the boundary of P, right, of f dot dl, Stokes' theorem says that's the integral over P of the curl of f dot dA, right? This is Stokes' theorem. But this only works in as much as there's no hole inside P. If there's a hole in P, all bets are off, right? If there's a hole here, that's a problem. That would speak to S not being simply connected. S is not simply connected. If there's some kind of hole in it, which if you take a loop and you try to deform that loop to a point, you get stuck on the hole. So a good example, what's that noise? Anyway, a good example of a space which is not simply connected, if you take like all of R3 and you delete the z-axis, this is not simply connected because if you have a loop that's around the z-axis, you can't pull it past, right? In 2 dimensions, if you have like the punctured plane, right? Remove the origin, right? If I have in R2 with the puncture, you know, if I have a loop that's around the origin and I try to deform it to this point, I get stuck on that origin. I can't deform the loop to a point. So if I take the plane and delete a point, it's not simply connected. If I take R3 and delete an axis, it's not simply connected. So the context that this implies conservative is that S has to be a simply connected space. All right? That's all I'm saying. Now, if that's the case, and that is pretty much going to be the case in our application, right? Because this is true where it's defined, right? So where would it not be defined? It's not going to be defined technically where there's like a localization of charge, right? So if I had like a planar charge, maybe we wouldn't have the curl defined on the totality of that localized charge. Or like the curl's not going to be defined at the actual line of a line charge. The curl's not going to be defined at the actual point where the point charge is, right? But if you think about that, I don't think those obstructions, ignoring the line charge, are going to make the total space not simply connected. And the funny thing is, this isn't like a, it's not, this theorem is not, this theorem doesn't say more than it says, right? What this says is that the vector field is conservative if the space is simply connected. It does not say, on the other hand, that if the space is not simply connected, it's necessarily the case that it's not conservative. It may still be possible to find a global potential for the vector field, all right? Now, the first three do not require the curl thing at all. And so for the first three, like the way that this field, the way the potential in the sense of calculus 3 is built, is you just integrate from some reference point, R naught, to your point R of f dot dl. And you can prove that that implies that the gradient of little f is equal to big F. This would be assuming that, you know, R naught is an element of your space in question, right? So you can actually construct the potential function for a conservative vector field by calculating this line integral, right? So this is just, I'm just giving you guys a very quick rehash of like the relevant part of Calc 3, all right? Now let us return to our regularly scheduled Griffiths, all right? So my takeaway from all this is that the curl of the electric field is equal to 0 implies that there exists V, right? A mapping from, you know, R3. What am I doing? I'm so sorry. I'm polluting this physics lecture with math jargon. So let me stop this. Don't tell Dr. Budaris. So, you know, there exists, we can find a V such that, here's what we say in physics, scalar. There. Now it's physics. Scalar function, right, such that the electric field is equal to minus the gradient of V. All right, now we put that minus there. We put that minus there for the same reason we put the minus there in like physics 231, right? We say minus the gradient of the potential energy function. Why? So that ultimately, so that kinetic energy plus potential energy is conserved, right? So this minus is here so that we can interpret later, when we talk about energy, the potential as potential energy per unit charge. If I didn't put the minus there, I don't know what we'd call it, but it wouldn't be what it is. Okay, so that minus has to be there. And with that minus there, we have, you know, things we can say like the voltage. Oh, by the way, we call V voltage. It's, you know, if we're going in the direction of the electric field, we're going opposite the gradient of the potential, right? The gradient of the potential points what direction? Yeah, the gradient potential points in direction of increasing V, right? So this means that if the electric field is minus the gradient, then E points towards direction in which V decreases, right? So in other words, the electric field points in the direction of decreasing voltage. If you put a positive test charge and you let it, you know, be influenced by an electric field, it's going to push it to lower voltage regions. You guys remember this from the previous course. Great. So how can we calculate the potential from the electric field? Yep.
What does ST mean?
Such that. So if you follow the thread of calculus 3 as it interacts with this course, we can also define or calculate, depending how you want to look at it, the voltage as equal to the integral from some origin point to R of E dot dl. Now that's wrong. If I was to write that formula, that would make E equal to the gradient of V. But it's not, right? So like in Calc 3, we do this thing over here, right? Integrate F dot dl, that gives us the potential, because the gradient of the potential is the force in Calc 3, because students are lost enough without putting a minus into this, right? But in physics, we like to confuse students more, so we stick a minus in here, and that minus is necessary because it's going to give you that minus over there. Putting a minus there means that this implies that the gradient of the voltage is actually equal to minus the electric field. All right? And that could be derived, but it's not especially interesting to this course. But essentially, you can exploit the path independence of the electric field, and you can go on a little horizontal path and a little vertical path, and you can derive that the gradient of V has to be E. Yeah, minus E.
What's the symbol below your
Origin. That's my current symbol for origin. I won't recreate it, right? So let's see here. Example 1. We could have like electric field is, let's say, E naught Z hat. Then if this is the case, I can make my voltage equal to minus E naught Z, right? Then the gradient of V will be minus the gradient of V, minus oh, I'm sorry, I get out of the way here. Whoa, goodness gracious. Minus the gradient of minus E naught Z, which E naught being a constant gives us E naught times the gradient of Z. But the gradient of Z, we know, is Z hat. So there you go. Now I have not derived. Now if I do this, what's, where's the voltage 0 for this? So I'm saying V of, to be more clear, V of x, y, z equals to minus E naught Z. This is a voltage function that works for this constant electric field. In this particular one, the place where the voltage is 0 is actually a whole plane. That doesn't usually happen, but for this one, you could reasonably take the origin to be any point in the z equals 0 plane. All right. What if we have like Q at the origin, right? So in this case, the electric field, you know the deal. It goes, outward, Coulomb field, here it is, right? E equals to Q over 4 pi epsilon naught, R hat over R squared, right? If I take a path that goes from out here at infinity, let's say, and it goes in like that, right, to this point, let's say R. I think he starts, well, anyway, I'm going to try not to worry too much about he's got some stuff about primes in the book. I haven't quite wrapped my head around what he's saying yet. I think it's just the age-old, don't use a variable as a fixed but arbitrary meaning and use the variable as the integration variable at the same time. I think that's all that's going on, but anyway. So what I'm saying is, let this be let way out there be your origin. Your potential is 0. So V equals to 0 out here. And then we want to look at this, we're going to let V of r equal to the integral from out there, there's a minus here, to that point r. And then we've got E dot dl. Okay, I think I know what he's talking about now. He just wants to put primes on here because he doesn't have a prime here, and he's going to want to use r spherical coordinates for doing the calculation. So like this, if we look at dl, what's dl in this case? It's something like, minus dr r hat, right? Because we're decreasing as we go in there. And maybe we should put maybe we should put like a prime here. Prime, 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 primes all around. All right. I almost feel like putting a prime on the point we're trying to calculate the voltage at and leaving unprimes off the integration since we're doing more of that, but maybe that's what he did. I don't remember. The point here is we're integrating from infinity to r, and we've got q over 4 pi epsilon naught r hat over r squared, right? Dotted with dl prime. Well, dl prime is minus dr prime. I can't, guys, I'm sorry. I can't do it. Let me, forgive me. I'm unpriming this. I'm priming that. That's just better. Yowzers. Anyway, so there you go. There's your dl. Of course, the dot product of r hat with r hat is 1. And we're left with, the integral from infinity to r of r prime, I guess, of, I'll get it eventually, q over 4 pi epsilon naught dr over r squared. Notice the minuses canceled. If I didn't do this wrong, I hope I'm not talking myself into the wrong formula. We'll find out soon. No, I seem to have found a way to put an extra minus in. Well, the answer is supposed to be 1 over r, not minus 1 over r.
Does it have to do with your integral bounds? Get backwards.
What's the direction?
But the integral does go from the origin to the field point. Here the origin's like the place where we're taking 0 to be the voltage to be 0 at infinity, and I'm trying to find the potential at r prime here.
Wouldn't that create a negative? Would that mean you need to flip it?
And
I don't know.
What's the dl equals negative dr?
well, my thought was that it should be that because we're going this way, and as I understand it, r hat goes that way. So it seems like I need a minus here because we're going in that direction for dl. But I think he just says dl vector is, I mean, he somehow has, all right, I don't understand why I'm wrong at the moment. Let me just, I don't there's something I'm confused about here. I'm sorry, guys. I don't know what there's something I'm like double counting in terms of signs. And I don't quite understand how I did that, but anyway, I've done worse things today, so here we go. So the voltage, I mean, the proof's in the pudding. Like the formula he derives, it works, all right? So he's definitely right, and I'm definitely wrong. I just don't know why I'm wrong, all right? And so that gives us a Q over 4 pi epsilon naught r. You evaluate that from infinity, r prime rather, to r, and that is just giving us Q over 4 pi epsilon naught r. That is the voltage for a point charge. So setting aside my stupidity, the voltage at position r is going to be given by, Q over 4 pi epsilon naught script r. This is the voltage, potential rather. For point charge at r prime. So here, as usual, script r is r minus r prime, and script r, that's the length of the separation vector, right? So, I mean, the example two, I've almost showed you the argument for why the voltage, if we calculate the line integral properly of the electric field, all right, it works out to that. Now this supposes that, I mean, I find this very dissatisfying as a student, honestly, because we're saying the origin's at infinity, but this obviously begs the question of, in which direction? What do you mean at infinity?
Well, only the r-hat direction matters. That's what that product.
Well, that's the thing is, like, is it infinity over there? Is it infinity up there? Is it infinity over there? Like, which direction infinity? Yes?
Couldn't you just make any rotations you feel like in the best work?
Couldn't I make any rotations? Wait, what?
I mean, if you like rotate in a circle around Q, it doesn't do any work.
Yeah, but I mean, shouldn't the origin be a point?
Just a one-dimensional point.
I mean, it bothers me. I think the answer to this bothering I have is that it's going to be okay as long as we're talking about a finite collection. As long as we're talking about a finite collection of charge, it doesn't really matter which direction we go. If we're infinitely far away, it's the same difference, whether we're infinitely far over there, or infinitely far up there, infinitely far down. Whichever way we go, we're infinitely far away, it's the same difference if the collection of charge is finite. Now, if the collection of charge is not finite, right, then you can't put the voltage being zero at infinity. It doesn't work, right? So we can only make the voltage zero. We can only adopt this convention of the voltage being, the potential being set to zero at infinity if we have a local collection. We don't have an infinite charge distribution, like a line of charge or a plane of charge. All right? Sorry, I will locate the source of the. I will find the demon. I will exercise him from my notes. Rest assured. All right. So listen, if this is the case, then in the same way we can define the electric field by integrating the density, we can. So this is for a point charge, right? But by superposition, we can also, for an extended a collection of charges, we can integrate this, right? Like so. my bad, like that. And this should give me the voltage for a continuous distribution of charge, assuming it's local, right? This presupposes that we can take the voltage at infinity to be 0. If I can't do that, I can't write this, all right? But in that context, I can write this. And of course, this is different things to different people, right? Like this, we have to interpret properly over a volume. We would do like rho d tau, right? Over 4 pi epsilon naught script r. And to be clear, it's supposed to be, done over the, to be fussy, this is over rho of r prime, right? That's the nature of the integration. And this is what? To be fussy, this is the length of r minus r prime, right? Or, it's not equals, but I really should say it could be interpreted this, or it could be interpreted as the integral over a surface, right? Sigma of r prime, dA prime, divided by 4 pi epsilon naught script r, right? Or the integral over a curve of the charge density, linear charge density, like lambda of r prime, ds prime, or dl prime, I guess, is his notation. It's an arc length integral, basically. So depending on whether we have a volume, a surface, or a line charge, we can do these integrals, these scalar integrals, and calculate the voltage. For example, well, this is the funny thing. It's like, yes, you can do these integrals to calculate the voltage, and it's not too bad to actually to carry them out. But it's often much nicer to find the electric field and work backwards through integration. Like as a point of, calculational ease, there is another way to go here. So yeah, I mean, we can do these calculations, and maybe it's even good to do it. Let's try. Let's go back to the, where am I? Example 3. Okay, so let's see if I can make quick work of this one. What if we have rho of r equal to, let us say, q over 4/3 pi r cubed, 0 less than or equal to r less than or equal to big R, and then 0 outside, right? This is what? We played with this example last time, right? This is the uniformly charged sphere. So if I'm trying to calculate the voltage at R, I just need to integrate, rho and d tau prime, right? Divided by 4 pi epsilon naught whoa. Maybe this is worse than I thought. All of a sudden I have a bad feeling. I thought this was easy. I'm not so sure this is easy. Goodness gracious, guys, look at this. I mean, the d tau prime, I can be more explicit. This is, r prime, oh goodness, the primes are killing me. R prime squared, sine theta prime, oh gosh, it's horrible. Theta prime, d theta prime, d phi prime, d r prime, yay. And this is, integrating. We integrate from 0 to r. We integrate from 0 to 2 pi, right? Integrate from 0 to pi for my theta, since this is physics. But golly, I mean, this is, okay, this is not bad. The rho is constant, right? We could pull that out here. That's just, we could call that rho naught. You know, this quantity we can call rho naught, right? But
Because you can separate those integrals into one that's sine theta, one that's like maybe a chain rule.
well, oh, you're saying that this is really just like square. Well, I regret erasing that.
Yeah, because you have something in terms of prime squared. I don't know if there's a chain.
So here's the thing. Last time we found that the electric field, right, was what? Goodness gracious, it was equal to. So fine. At the moment, by the way, I'm assuming that r is less than or equal to r in this calculation. Otherwise, that's the thing. Is like we're going to have to, this calculation has to break into two different cases. For the radius being inside the charge distribution, the calculation is different than if the radius is outside the charge distribution. We worked out last time that the electric field was, yowzers, Q r over 4 pi epsilon naught r cubed, I think. Was there a 3 up here? You guys have to remind me. I don't have my notes on me.
I had to have rho in there somewhere. I think it's a.
I mean, this has to reduce to the Coulomb field. This has to reduce to the Coulomb field when we get r equals to r. So I think it had to be that. But then, of course, outside, this is just Q over 4 pi epsilon naught r squared r hat, right? So I think that was it. I know it's linear from the origin. Yeah, I know it's linear from the origin. I know it's 0 at the origin. I know it has to be equal to Q over 4 pi epsilon naught big R squared at the edge. So this has to be the formula. So my point to you is calculating this integral, I don't want to do. It's actually much, much easier to say this is minus the gradient of the voltage, right? And just work it out. See, because I have V of R. So if we're assuming the voltage is 0 at infinity, let's do the infinity case first. So we just have Q over 4 pi epsilon naught 1 over R for R greater than or equal to R, right? That's the voltage out there. And how do you find the voltage inside the sphere? You need to integrate this, right? So the integral of this is 1/2. Well, it's Q R squared over 2. My bad, I can't integrate. Integral of R is R squared over 2, so I get an 8 pi epsilon naught big R cubed, right? But I need to add a constant here, right? I have to add a constant. Let me call it C1. And what's the deal with that constant? How does it have to behave?
So the surface has to be the same.
Right, the voltage has to be continuous on the surface is the thing we can argue. All right? So we have to be able to fit, like the voltage on the surface. So we basically have to be able to solve Q divided by 8 pi epsilon naught R squared. That plus C1 has to be equal to Q over 4 pi epsilon naught R. Whatever C1 solves that, that's the C1 you're looking for. So, all right, because the voltage has to be continuous. Why does the voltage have to be continuous? What does it mean for the voltage to be discontinuous?
The electric field is undefined.
The electric field is undefined. Yeah. Well, the voltage would have to jump, wouldn't it? Yeah. If the voltage jumps, if like the voltage has a jump discontinuity, that means the gradient has like a direct delta, which means the electric field is infinite, I think. Right? So a discontinuity in the voltage indicates an infinite electric field, which could cause problems, I suppose. All right, so there's a circle of ideas that I'm trying to get after here. So I'm sorry I don't have better calculations to share with you guys today. I have run short on time, and I'm stuck. Well, first of all, I burnt a bunch of time trying to prove that lemma. That lemma is not easy to show, and I still don't have a full convincing calculation of it. Griffiths has a way around it, which is kind of sketchy. He just shows that the curl of like a single point charge based at the origin is 0, sorta. And that's fine, but I really need that lemma to hang my hat on the rest of what we're doing here. So I'm going to have to prove that lemma to make myself feel better about this material. But that aside, let us move on. So we have the electric field is equal to minus the gradient of the potential, right? And our goal in the next part of the lecture today and next class is going to be to understand what are the properties of the voltage function, what are the properties of the electric field, how are these related, how do we get from one to the other, what's the circle of ideas altogether here, right? So the first thing we should notice is that the divergence of the electric field is then the divergence of minus the gradient of the voltage, right? So we have a notation for that, which is minus nabla squared V. This is the so-called Laplacian of the voltage, or the potential, Laplacian. And it kind of depends on which book you look at. Some people use del squared, some people use minus del squared for the Laplacian. It kind of depends, just like what book you're looking at in junk. But Gauss's law in differential form said this is equal to what? It has to be equal to what? Rho over epsilon naught, right? So this right here is Poisson's equation. So Poisson's equation says that the Laplacian of the voltage is equal to minus the charge density divided by epsilon naught. So essentially, the problem of finding potential for a given charge distribution is the problem of solving this second order partial differential equation. Now, this is the province of chapter 3 in Griffiths. That's all we look at that as a problem of partial differential equations, and we solve it with the techniques that are warranted there. At the moment, though, you see one of the direct solution to this, I've already written on the other board. The solution is V of r is equal to minus the integral from whatever your origin point is to r of rho of r prime d tau prime divided by, 4 pi epsilon naught, the distance from r to r prime. Like that is straight up the solution to Poisson's equation. And as I was reminding myself, that's lovely. It's a lovely thing to write, but it's also sometimes a monstrous thing to calculate for certain distributions. So like as a general point of order, if you can calculate the electric field from Gauss's law, it's nicer to do that and then work backwards to the potential from the electric field. That's kind of like a good point of calculation order. So let me see here. Now he does actually have the calculation of the, he does calculate the voltage. One of the examples in Griffiths, which is kind of intriguing, is he does for, sigma constant at R equals to R. So if I draw a picture of this sort of two-dimensionally, the picture is there's only charge at that radius, all right? And then, so he's just got this like very, very infinitesimally thin shell of charge here, all right? And so he actually, in Griffiths, he actually works out this integral for that distribution for a uniform. It's about a page of calculus. It's kind of ugly. Let us see if we can work through that problem using the Gauss's law idea instead. So what is the electric field for this? So again, the charge density, it's just a spherical shell of charge. And we're going to say, net charge Q to make things nice. Right? So that makes sigma's what then? What's the surface area? 4 pi r squared. Cool. Very good. So I'll do the easy part. If we draw the Gaussian surface in here, lo and behold, we've got the flux of the electric field is equal to the charge enclosed over epsilon naught, which gives us that we've got 4 pi r squared E is equal to 0. E is equal to 0 inside, right? By the spherical symmetry, we have 0 electric field inside the charged sphere. How does Gauss's law work outside? What have I done? Is it time? Okay, so I think we started like 5 minutes late. I will wrap this up. This is our final example. So the electric field outside, by Gauss's law, is the Coulomb field, right? So the voltage function in this case, there's 2 cases, all right? On the outside, the voltage is Q over 4 pi epsilon naught 1 over R. This is for R greater than or equal to R. And what's the voltage inside? What can you tell me about inside? Gradient of the voltage inside the sphere, right? What is it equal to? No. The gradient of the voltage is minus the gradient of the voltage. What's it equal to? Does that help? 0. It's the electric field. It's 0. Calculus 3, what does it mean when the gradient of a function of several variables is 0? What's that say about the function? It says the function is constant. So the voltage inside the charged sphere is constant. And what is that constant? By continuity, it has to be this. So the electric field is discontinuous. Right? If I draw a graph, R, then the electric field, it starts out here and it drops off inverse square. Right? And then the electric field in here, 0. Why is there a jump right here? Because at R, there's charge. But the voltage, nevertheless, must be continuous. And the voltage I guess it's kind of more, I mean, it's different units, right, whatever, but the voltage is, you know, however, you don't have to start at the same point. Let's say this is the voltage here, whatever. And I'll draw it under here just for the sake of convenience. It drops off like reciprocal out there, right? But inside the sphere, it's constant. That's the voltage, the potential. The blue in my picture is the electric field. All right? So I'll try to explain more about how we have to understand the electric field going inside and outside surfaces, like the boundary condition idea. That's really new to this course, and it's not that complicated, but it's like once you understand it, you can derive everything that you were just taught, perhaps just as a kind of a rule of thumb in the previous course. So anyway, I shut up. Have a good weekend, you guys.